Hello students, welcome back to the ninth video of this playlist. In this video, we will be discussing question number 18 from the most recent past paper of Physics Unit 2, which is the October 2024 Unit 2 paper. So let's get started with question number 18. So here it says the photograph shows the Golden Gate Bridge in San Francisco, USA. Okay. The bridge has two main cables. Attached to these cables are smaller suspending cables which support the road. Okay, so we can see in the figure the San Francisco Bridge. Wind causes each suspending cable to oscillate, so standing waves form on the suspending cables. Fine. Okay. So part A here is asking to explain how a standing wave can form on a cable that is fixed at both ends. Okay, so we have to explain how a standing wave is formed within the suspending cables. Okay, so as a wave is formed within the cable, the wave will get reflected from the ends of the cable, right? Waves get reflected from the ends of the cable, from the ends of the cable, and are coherent. These waves are coherent because they are from the same source and they have a constant phase relationship with same frequency, right? Okay, so the coherent waves, since they are coherent, so the reflected wave, the original wave, and the reflected wave interferes inter uh, inter ha so the original wave and the reflected wave interferes. Okay, they will interfere with each other. So where they interfere, okay, the second point we said the original wave and the reflected wave interfere. So as they interfere, we know that in a standing wave there are nodes and antinodes. So now you have to say how these nodes and antinodes are formed. So where they interfere in phase, okay, constructive superposition happens. Constructive superposition happens, and so their antinodes are formed, right? Regions with highest maximum displacement is formed. So their antinodes are formed. Okay. Then where they meet or interfere, whatever you say, interfere out of phase, not out of phase, sorry, it should be antiphase, definitely. Interfere where they meet in antiphase. What happens? Destructive superposition happens. Superposition happens. Okay, happens. So there, what is formed? Nodes. Nodes are formed, and that's how a standing wave pattern, a standing wave is formed on a cable. That's it. Okay, next is part B. Okay, so in part B, the question says the diagram shows a standing wave on a cable that is fixed at both ends x and y are okay at both ends. So x and y are 2 points on the cable, x and y. Describe the motion of points x and y on the cable. Okay, x and y. How can we describe the motion? It is for 3 marks we can see here. So at first consider point x. So point x, we can see that it is basically at the point of maximum displacement, right? So we can say that describe the motion of points x and y. Okay. So at first, the first point x is at the maximum amplitude, right? It is at the maximum amplitude, right? So at point x, so point x of the cable, since it is at the maximum amplitude, so it will move through that way, right? It will go to minimum and then maximum like that, right? It will move left to right, right to left, isn't it? So point x of the cable will always have a displacement, will always displace from maximum to minimum and then minimum to maximum, right? Okay, so at point x, the displacement varies from at point x of the cable, the displacement varies from maximum to minimum. Okay, this is what we can say for point x. And at last, for the third point, we can say at point y is at the at the zero amplitude. Okay, is at the zero amplitude. Hence, it is a stationary point, or you can say it is a stationary point on the cable. Okay, because since it has zero displacement, so point y will remain as it is always. Okay, it will not move. Okay, but point x of the cable, it will displace from maximum to minimum amplitude. Okay, it will always have a displacement. So that's what we can write for part B of question number 17, question number 18. Fine. Okay, next is part C. So, okay, in part C, the question says, in strong winds, the Golden Gate Bridge emits a humming sound. Okay, so part 1 of C, it says one of the suspending cables on the bridge has mass 2.10 times 10 cube kg and a length of 87 meters. So it is asking to show that the mass per unit length mu of the cable is about 24 kg per meter. Okay. So the mass per unit length. So the mass is given, right? And the length is given. So mass per unit length mu equals to total mass over the total length, right? So total mass is 2.10 times 10 cube over the total length is 87 meter. So that would be that much kg per meter. Therefore, the value for mu, it is basically 2.1 times 10 to the power 3 over 87. So that would give you 24.13793103 kg per meter, which can be written as 24 kg per meter. Short. Fine. Okay. Next is part C2. So in part C2, the question says the lowest frequency of the humming sound produced by the bridge is 280 Hz. Okay. The total mass of the road on the bridge is 140 times 10 to the power 6 kg. The weight of the road is supported equally by 500 suspending cables. Okay. The range of lengths of the suspending cables is from 3.5 meter to 160 meter. Okay. So the minimum length of cable it is 3.5 meter. The maximum length of cable it is 160 meter. Okay. The value of mu for all of the suspending cables is 24 kg per meter. Deduce whether the lowest frequency standing waves on the suspending cables could be producing the humming sound. Okay. The lowest frequency. Okay. The lowest frequency. Okay. For standing wave, we know that the formula for standing wave it is F equals to 1 over lambda times square root of T over mu. So basically, the value for F, the frequency would be lowest, the least when the lambda is maximum. So the value of lambda it is basically dependent on the length of the cable, right? So for the length of the cable, we know that the minimum frequency, the lowest frequency, it is basically dependent on the length. So for the minimum frequency, we have to consider the maximum length. Okay, the maximum length of the cable, that is 160 meter. Okay, this is the lowest. This will give the lowest frequency. Okay, so in that case, we have to consider the tension T. The value for mu we know. The value for lambda it is dependent on the length. So definitely for lambda we have to consider the fundamental frequency. Okay, for finding the frequency we will consider the fundamental frequency, because fundamental frequency is the frequency of the first standing wave pattern that is formed within a string. Okay, so we will consider L 160 meter for that, and we will find out the fundamental frequency for that length. Okay, so for finding the fundamental frequency, let me write the formula. F naught equals to 1 over twice of L square root of T over mu. Okay, so we need the value for T. The value for the value for mu we already know. The value for lambda we will consider L equals to 160. Okay, to get the lowest frequency, and now we need to just figure out the value for T, the tension. Okay, so there are 500 suspending cables, right? So that means there are 500 tensions like this. There will be 500 tensions. This is one T, this is another T, this is another T. Like that, there will be 500 tensions which will be supporting the road and the cars on the road, whatever. Okay, so we will consider the forces acting on the bridge, okay, on the road vertically. So there are 500 ropes. So for 500 ropes, there will be 500 tensions. So 500 T equals to what's the weight? Weight is 140 times 10 to the power 6. Okay, so 140 times 10 to the power 6 G Newton. Okay, the weight of the road. Okay, so the tension in each of the cable it is 140 times 10 to the power 6 over 500. that would give you 2,80,000 Newton. Okay, this is the tension. We got the tension. Now, frequency will be lowest when L equals to 160 meter. That is when the length is maximum. Okay, so L equals to, we will consider 160 meter, and now for 160 meter find out the value for F0. So 1 over 2 times L, that is 2 times 160 square root of T over mu. The tension is 2,80,000 over mu, the mass per unit length of the cables. This is 24. That much hertz. So let's find out the value. 2,80,000 over 24, then square root of answer times 1 over 320. So this is basically 0.337538 something. Okay. Okay. So we got, okay, I didn't multiply that G with the value here. Okay. 0. Because 0.37337, it's not even a complete cycle of wave, right? So definitely there is a mistake with the tension. Please correct this out. 140 times 10 to the power 6 times 9.81 over 500. Now it is perfect. Yeah, it should be 27,46,000, not 2,80,000. That's a very small number. Okay. So 27,46,800, that much Newton. Okay. So please correct this out and put 27,64,800. Now please calculate. So it is 338 over 320. So this is basically 1.057201864, that much hertz, which is very smaller compared to the frequency of humming sound, which is pretty much less than 280 hertz. Okay, so we can make a deduction that the lowest frequency standing waves on the suspending cables cannot produce the humming sound. Hence, the lowest frequency uh, standing wave produced on the cable, on the suspending cables, could not produce the humming sound. Okay, that's it. That's the deduction we have